All right, let's talk about Chapter 6 in our textbook, specifically image quality and the determinations of image quality. We're going to look at the technical factors, different scanning parameters, as well as how to define image quality. So we'll talk about spatial resolution and contrast resolution. And for those of us who've had kind of brief reviews or some discussion of digital radiography, some of this stuff will sound pretty familiar. So, anytime we're talking about image quality, we kind of have to begin with thinking about the scan parameters, because those are the things that we have direct control over. So these are things like MA, scan time, field of view, the reconstruction algorithm. We can actually define what that reconstruction algorithm should be, as well as KVP and pitch. So typically we just refer to this as mass, milliampere seconds. So it's a certain amount of amperage over a certain amount of time. And this is what impacts the total exposure of the X-ray beam. So the amount of photons flying out of the tube is determined by the mass. Kilovolt P is going to determine the amount of energy that those particular photons have. So the one word that we kind of use to talk about mass is the quantity of the X-ray energy, the amount of X-rays that are being boiled off. And we can actually do calculations to determine at certain MA settings how many electrons or how many photons could actually be produced. And it's millions. It's hundreds of millions of photons are being produced when we turn this thing on. The higher the MA setting, the shorter we can make the scan time. So MA can, if we crank up the MA, we can crank down the time, basically, and have the same kind of technique. And specifically, a short scan time is helpful in avoiding kind of image degradation as a result of patient motion. We think about this a lot when we think about the history of X-ray. The very first X-ray exposures, like in the late 1800s, required like 8 minutes of exposure time, right? So patient motion was a serious factor at that time. So a lot of the early X-rays, like from, again, the late 1800s, were X-rays of things like mummies, X-rays of birds, things that aren't going to move while you're trying to shoot a picture of them, right? Now we're talking about fractions of a second. Tube voltage or kilovolt peak. We've talked some about how KVP very often is a peak in that there's like a rainbow, a spectrum of energies that's produced when we turn this thing on. So we can set a peak amount that we would hope all the X-rays would possess, but really what we're going to see is a spectrum of energies from everything below up to that point. So that's what we're talking about when we talk about kilovolt peak. It defines the quality of the X-ray. So again, another way to think about it is the power of the X-ray. One metaphor that people have used in the past is, imagine I had a shotgun, right? The mass is going to be the amount of buckshot in the shotgun shell. The kilovolt peak is actually the gauge of the shotgun. It's the amount of gunpowder that discharges and forces the gun pellets out of the shotgun shell. Does that make sense? So in CT, KVP does not change contrast as directly as what we see in film screen radiography, because CT is, again, a digital system, and it has a straight line relationship between between X-ray energy and detector detecting the X-ray energy, if that makes any sense. So as compared to, we're going to have a whole broad range of MA settings that we can set. In fact, we can even have the machine automatically determine what the MA should be. But KVP is going to be 2 or 3 options, period. Like it'll be 100, like 90 KVP, 100 KVP, 120 KVP, and nothing more than that, right? You're just going to have those 3 basic options, and that's kind of across the board for all CT scanners, regardless of who made them. So these things have a direct tie to the radiation dose, and what we're really trying to shoot for is a way to optimize the image, right? So I can crank down the mass and get crappy pictures all day long, right? So the name of the game isn't necessarily to keep patient dose to an absolute minimum. It's a balancing act between image quality and patient dose. So we want to find the best possible picture at the lowest possible dose. Okay? So typically MA is more flexible, and we will actually be altering MA based on the image quality or the noise that we're getting from the detector. That's what these automatic tube current modulation things are doing. One thing that she talks about is this uncoupling effect. She mentions it briefly in the textbook, and it's interesting because this is in contrast to film screen radiography. If you're not familiar with how film screen technique works, then this may not be as clear. So I'll try to clarify it to some degree here. Basically, for CT and for digital radiography, image quality is not directly linked to dose. So even when an MA or a KVP setting is too high, we will still get pretty pictures. In the past, with film radiography, you could actually burn the image out. You could get, the technique could be too hot, right? And then you would no longer see an image. With digital radiography and with CT, because it's using a computer detector to detect the remnant beam, we cannot burn that computer detector out. It just continues to detect. It will just keep on detecting. So we can have a dose that's too low, but we can't have a dose that's too high. And so what she's calling the uncoupling effect, sometimes we call dose creep, where the radiologists, the radiographers understand that I can't burn the image out, but I can make it too light. So I will burn the image out. I will overexpose the patient in order to make sure I always get good pictures and the doctors aren't yelling at me. Okay? One way to think about it graphically is with film, we had what we called a characteristic curve. So it's kind of an S curve like that, and we knew that below this level we wouldn't get good pictures. Like below here we wouldn't get good pictures, and above here we've burned it out. So the pictures we're taking were in this range of energies, okay? And the contrast of the images were related to that slope there on that characteristic curve. What we see with digital radiography and with CT is something more like this. We just see a straight line portion. There's a point below which we're not going to get good pictures, but there's no upper bound to it, okay? The interesting thing about this is we can, if we understand this, we can use it kind of for the good. Like there's a light side of this and a dark side, right? The dark side, like the Darth Vader side, is this side over here, right? Is I know that if I burn everything out, I will still get good pictures. I might be giving my patient 10 times the dose that they need, but no doctors are going to be yelling at me, right? The light side is the folks who are over here trying to find this lower bound where what's the absolute minimum amount that I can give the patient and still get good pictures. Okay, this is a powerful tool. Automatic tube current modulation is a powerful tool in helping us establish that in CT. A related thing in diagnostic X-ray might be automatic exposure control. In radiation therapy, I know that as you're taking portal images, it has a similar kind of automatic exposure control where it cuts off the portal imaging system when it's received enough intensification to make an image, right? I don't know if there's a related kind of concept in nuclear medicine, so if y'all think of something, shout it out. But what this is basically allowing the technologist to do is to match MA to a noise level, right? So what I mentioned earlier is I can drop MA and get you crappy pictures all day long. The reason those pictures are crappy is because they have a lot of noise, right? So what we can do instead is to say, here's a range of energies I want you to use, machine. I want you to use this range of energies, and if the images start to get too noisy, crank up the juice and make them less noisy, right? And then if there's plenty of signal there, crank it down some, right? And so we call that automatic tube current modulation. what it would look like in the CT program is I'm setting up a protocol. I would have a little window here where I could define, I want my MA range to be from 50 to like 100, right, as I'm scanning. And then I'm going to tie that to some acceptable amount of noise. So typically this is expressed in a percentage, right? So let's say I want to maintain a noise level at or below 30%, right? So the machine is going to try to maintain a noise level at or below 30%, and it's going to work through those range of energies to determine that, right? The way that typically looks from, again, from a graphic point of view, and this is one of the reasons why it's important as you're doing, oh my goodness, what have I drawn? I need to draw this guy a little bit differently. Oh, Lord. So if I'm x-raying this mummy here, who's wearing a false beer belly, the machine is going to be getting like kind of a feedback loop of information from this. So it's going to be really, really important if you're using this kind of program to, when you do your scout images, for there not to be any shielding or car keys in the person's pocket. We want to, again, even though I can see through that, please remove your cell phone, your wallet, your car keys before you go into the CT suite. Because what it does is when it does this initial scanogram, like this scout image, if it sees car keys in there and it sees that area of whiteness on the scan, it's going to automatically crank up its dose. It knows, okay, there's something there that I need to see through. Maybe it's a hip replacement. The machine's going to project something into that and know, okay, it's just looking at levels of white and black on this image, but it's going to say, I need to crank up the juice there, right? It's already pre-planning that. So you kind of have to, I almost think about this thing like the Terminator robot. You have to kind of outthink the Terminator robot a little bit. Have the person basically naked except for a gown when you're in the CT room. Don't put any shielding on them, and then shoot and then do your scout images. Okay? Because it's going to go ahead and start calculating its automatic tube modulation based on that scout image. Right? It'll also calculate some of its iterative reconstruction protocols off of that scout image. So if you forget everything else I say today, know that one of the best ways you can reduce your patient's dose is understanding that the machine does these calcs off of the scout. So no shielding, no glasses, no hearing aids, no car keys, especially no car keys, in the CT scan room. The other thing that's really, really critical, let me think. There was one other part to that and it just went right out my mind. Let me kind of trace out to you what the machine is going to do with this information real quick. Okay, so we've told it a bound for an area of MA, and I'm going to draw on this image kind of how it's going to fluctuate MA based on that. So as it's scanning through, say we're scanning this person from head to foot, right? And this little red line is the amount of MA that it's using. When it gets to this point here, it's going to start cranking the MA up, right? And then it will crank it back down automatically based on the amount of noise that it's receiving as it's scanning. Okay? So, another thing that we have direct control over is the slice thickness and the field of view. Now, some of this is going to be determined by the protocol. So, before we start messing with the slice thickness, we need to be considering, okay, what are we looking for? How best can we image that? What is our protocol for this? Field of view, we have some direct control over. So for field of view settings, we can actually dial in what the field of view is for the scan. And that is simply a matter of giving it limits to the area that it's scanning. I don't need to crank it out to the entire scan field of view. If I can reduce it down and without clipping any important anatomy, I should do that, because that is actually going to wind up decreasing my pixel size. Right? The bigger I make that scan field of view, the bigger the pixels will have to be, so I will lose information. I'll lose spatial resolution. So let's talk real quick about slice thickness. We're primarily interested in slice thickness, so how the data is acquired, rather than the image thickness. Image thickness is something that we can control in post-processing. Slice thickness is actually how much the scanner progressed as it took every single image that it acquired. Okay? This of course, as we can imagine, has impacts on spatial resolution as well as patient dose. The smaller the slice thickness is, the higher the patient dose will be. Okay? Scan field of view and display field of view also relate to spatial resolution, and specifically the amount of area that it's acquiring raw data. Okay? So what does this look like from a scanning point of view? Again, when you do that tomogram or that scout, and here's your guy, oh my goodness, it looks like an airplane or a space shuttle. You can determine on it the area that we want to scan. I can set my display field of view on there, right? So if I give it a nice small area, it's going to get better spatial resolution versus if I have a bunch of area like this on it, it's not going to be as helpful. And I just remembered the other thing I wanted to say on the other slides. Another significant thing for this, right, in terms of how we're planning these things and how the bearing that it has on image quality and patient dose is this imaginary point right here called isocenter, right? We want the isocenter as much as possible at the center of the anatomy of interest, right? At the center of the anatomy of interest. So, for example, little old lady with a kyphotic back, you know, when I lay her down on the scan table, her head's going to be way up here and her body's going to be down here, right? Because she lays like that all the time. So if I'm scanning her head, I'm going to lower the scan table to where her head is in the middle of the isocenter for the gantry, right? If I'm scanning her thorax, I'm going to raise the table up to where her head is nearly hitting the gantry, and I'm going to center on her thorax, right? Those people can make life very interesting, but it's important for the scanner that the volume of interest is at the center of the scan field. Okay, so we can tie, to some degree, our reconstruction algorithm to the pitch. We discussed reconstruction last week? Is that what we talked about? No, we haven't. We're going to talk about that next week. I'm sorry. Last week we had our midterm. All right. We will get more in depth into reconstruction and reformatting next week. But just understand that the way that we reconstruct the images has a direct bearing on what the pictures look like. We can actually construct spatial resolution, increase spatial resolution into these images. Okay? So pitch is the amount of table movement per rotation of what? The tube. Yep. So this is another way of talking about slice thickness versus table travel. Okay. So again, this is going to have some bearing on spatial resolution. The higher the pitch is, we're going to see a fall off in patient dose, and we'll also see a fall off in spatial resolution. Okay. When we talk about scan geometry, these things are having less of a bearing on image quality than they did in the past, because now we're starting to model scan geometry into reconstruction processes. Okay? But basically, when we talk about scan geometry, we're talking about how much the tube rotates per each movement of the table, right? There are some scanners that will do like 400 degrees an overscan, basically, an overscan of the anatomy for each table movement. But primarily what we're dealing with when we talk about scan geometry is this guy right up here, the full scan, 360 degrees for each table rotation, for each table movement. Okay. Image quality is something that applies to all types of images, but it is largely a very difficult thing to define. Okay? One way to think about it is the comparison between the image and the actual object, bearing in mind that I cannot actually see the actual object because it's like the person's heart or their lungs, right? So in most discussions of quality, it is a subjective notion, right? And I know the X-ray folks have heard me talk about this, But this is one of the things that separates us in diagnostic imaging from, for example, nursing, right? Nursing has a lot of objective goals that they are trying to apply their understanding to. Like, for example, the patient needs to have this drug and this test or the patient dies, right? If these objectives are not met, then patient dies, right? In CT and in diagnostic x-rays, I'm dealing with subjective criteria. So if I don't do this, this, and this, I get crappy images, right? So to some degree, we are allowed to think more creatively about what we do than, for example, doctors or nurses. This is a fundamental, like foundational, philosophical difference between us and the majority of other people in healthcare, right? When you walk into a room with a doctor and a nurse, their objectives are very, very clearly defined in their mind. They almost have like a recipe checklist that they're going down. When I walk into the room, I'm looking at, okay, what's the best possible way to get this person to lay on my table? What's going to be the best perspective that I can shoot from? What will be the technical considerations I'll need to apply? I'm almost thinking more artistically about it, right? There's no right or wrong answer to the stuff that I'm thinking about. There are right or wrong answers to the stuff that they're thinking about. So I want you just to be aware of that, that as a CT tech, as an X-ray tech, nuke med, radiation therapy, we're allowed to apply what we're doing more artistically, more creatively. The main thing, though, at the end of the day, is did you get a picture that has diagnostic quality? Is it something that I can look at, and if there's pathology present, I can make that determination, yes, there's pathology present in this image. If I make an image that in some ways obscures pathology or doesn't indicate where the pathology is at appropriately, like for example, I produce a CT image that says there's a mass in the left kidney, when in reality I didn't flip the thing correctly and the mass is in the right kidney, that's a problem. Right? That's a big problem. So, nevertheless, for our purposes in this, we're going to talk primarily at what kind of objective measures we can define for making sure we get a pretty picture. Okay. The two main things are spatial resolution and contrast resolution. And I know that the X-ray folks are sick of hearing me talk about this stuff. But spatial resolution can be defined as the ability to resolve two separate objects, right? And typically they're high contrast objects. In the world of CT, we're going to use a special kind of phantom to make that determination. Contrast resolution is the ability to differentiate between objects that have different densities, but they're very, very similar densities as their background. And a good example of spatial resolution is, for example, the bones of the inner ear, those little tiny bones inside the inner ear, or the mastoid air cells inside the temporal bone. Can I distinguish those little tiny bony structures in the temporal bones? Right? That would be a good example of spatial resolution. There's a whole lot of those little things all together. Can I determine where one ends and the other one begins? An example of contrast resolution in the human body would be the liver. The liver has a whole lot of weird different things going on in it. For example, if a person has a tumor in their liver, it will be more or less the same attenuation value as the liver itself. And so it can be very difficult to distinguish between the contrast of the liver and the contrast of that tumor. Okay? And so for the purposes of CT phantoms, we are going to put a plastic thing inside the gantry, and we are going to scan through that plastic thing. And inside of that plastic thing, we are going to see different kinds of objects that can represent different kinds of measurements. That's why I want us to look at ROIs, placing ROIs on this stuff today. So for example, with a standard phantom, X-ray phantom, what you're going to get is an axial slice of something that's perfectly round. Right? It's a cylinder. It's a big plastic cylinder. And inside of this cylinder, I'm going to have some little tiny lines like this, little tiny lines like this, and maybe some lines that are more spaced out like that. Right? So I'm going to put an ROI over this area here and make a measurement. And basically, the measurement for that should match like the measurement here, because it should be able to differentiate between those sets of lines. Okay? Versus if I'm making a measurement, so this would be for spatial resolution. Over here, if I'm trying to measure contrast resolution, I might have simply a phantom that's full of water, and I'm just going to put an ROI right in the middle of it, and maybe right at the edge, and I'm going to see if it can determine that those are basically the same exact measurements, right? Because it should not make any difference between whether this ROI was placed in the middle of the material or at the outside of the material. It's the same material. It should have the same Hounsfield unit measurement. Okay? Spatial resolution. We might also call this detail resolution. We will use, again, those line pairs in the phantom to measure this. And then we may actually apply this to a modulation transfer function. This is one of the fancy ways that manufacturers sell you the coolest new CT scan, is they show you in a modulation transfer function how much spatial detail is apparent even as the line pairs increase, okay, or the size of the object decreases. So the way it's represented graphically, it's in our textbook, but a lot of times it looks like this. Over here on this side, let me find where it's at in our textbook real quick, page 63. Over here on this side, we'll have some kind of MTF that's telling us how much resolution is visible. And then over here, we're going to have spatial frequency. So this is how small is the little things that we're trying to get. So the frequency, as the frequency increases, the size of these things are decreasing. Okay? As the frequency increases, the size is decreasing, so what we'll see is a graph that looks something like that. Okay? We want to see these curves go further and further out as possible, and that's going to mean that that scanner is that much more capable of delivering quality spatial resolution. There's two different ways, or two different dimensions in which we might talk about spatial resolution. There's going to be in-plane resolution, so that means within the scanner plane, so that's the X and Y direction, right? Then there's longitudinal spatial resolution. That's going to be along that the Z-axis, and so it does have relationships to pitch. Okay? As I mentioned before, matrix size is going to have a really big determination on spatial resolution, so we want to keep our display field of view small. Okay? Most matrix sizes for CT scanners in general are 512 by 512, right? That is pretty much standard. So we want to keep our display field of view small because we don't have a very big matrix that we're dealing with. Keeping our display field of view small, we'll keep our pixel size small. If I could write here. We also want slice thickness to be as small as possible. Reconstruction algorithms will have some impact on spatial resolution, and we'll talk about that more when we talk about actual reconstruction. Focal spot size, again, we want it to be small. Pitch, we want it to be small. And we want no motion. None. So, in terms of if you have a patient, they want to know what they need to do, you really just need to hold still. Make sure you listen to the breathing instructions. The best thing you can do is you can explain to them, the machine's going to talk to you, it's going to ask you to hold your breath. When it says hold your breath, I want you to do this. And that's it. I don't need you to talk to the machine. I don't need you to get up and start flailing around or puking on the machine or anything like that. Just hold your breath. Be nicer than I am. Contrast resolution. We might also call this contrast detectability, but generally I call it contrast resolution. CT is superior in terms of contrast resolution to pretty much every other modality. Its ability to resolve contrast is what gives its increased sensitivity and specificity. It has higher contrast resolution than medical X-ray. It has higher contrast resolution than pretty much anything else. So, for example, in medical radiography, for an object to be differentiated from another object on an image, on an X-ray picture, they need to have at least a 5% difference in contrast. They need to have at least a 5% difference in their linear attenuation coefficient, right? For them to be distinguishable on CT, they only need a 0.5% variation. So I can see very, very carefully, is that a mass in the liver or is it just liver? That's what we're talking about when we talk about sensitivity. How sensitive is it to different attenuation coefficients within the anatomy? So we are going to use phantoms to measure this. And inside the phantoms there will be little plastic pieces that have very, very small differences in their Hounsfield units. Very, very small differences in their attenuation coefficient. And we are going to measure that. In addition, we are going to measure noise. Noise is probably the #1 limiting factor to appropriate contrast resolution for CT imaging. Because of the way the reconstruction algorithms work, when it's sampling a volume of interest, right, from the CT scanner point of view, because it samples it as a continuous function, it's sampling continuously as it spins, right? If there's some kind of noise, if the patient has keys in their pocket, it is going to keep that noise throughout the entire sample. It cannot say at what point do the keys can I say the keys are in the person's pocket. It never says that. It just says there's always noise. There's always noise. So we have to figure out a way after the fact to let the machine know just because there's some noise right there doesn't mean the entire thing is noisy. So because it's a continuous function, it's going to uniformly distribute noise across the entire set, right? But through iterative reconstruction, through new reconstruction algorithms, we can say, no, the noise is only right there. Get rid of it on everything else. Don't sample it as a continuous function. So we'll look more at that. But in general, what we're going to see is fluctuation in pixel values. It'll give it a grainy or a salt and pepper appearance. Okay? Sorry, I'm thinking about that commercial now with salt and pepper in it. Okay. Factors affecting the contrast resolution are going to be the mass or the patient dose. So for filter back projection, which is the predominance of what CT used to be, at least when this textbook was written, mass dose was directly tied to noise. As I decrease my mass, I increase my noise. If I want to decrease my noise, I need to increase my mass. They're inversely related. Okay? Pixel size. As I get my pixels, I want my pixels to be smaller in order to have better spatial resolution, but as I drop my pixel size smaller, the noise will also increase. Okay? Slice thickness can impact contrast resolution. Reconstruction algorithms, as I just mentioned, and we'll talk more in detail on that, I think, next week. And then patient size. As we get patients who are bigger and bigger and bigger, we're going to see more noise. We will have a reduction of contrast. If we have a patient, for example, who's pushing the table limits of the CT gantry, even if we were to give them IV contrast, we might not even be able to see that contrast on the images because it's all being absorbed by tissue. So, other things to consider are the actual subject contrast. As I mentioned earlier in the semester, I think the patient has an amount of contrast within that volume of interest. So, for example, the thorax has a high subject contrast because it has air in the lungs and calcium in the bones. There's a lot of subject contrast between those two things within the patient. So, for example, whenever I'm scanning the thorax of a patient, a lot of times I don't even need IV contrast to see what I need to see. There is inherent contrast, and that's going to be the physical properties of the object and its background. Inherent contrast is something to think about again, maybe that liver. The liver versus the spleen. They have a inherently different contrast, and that's how I can say that's liver and that's spleen. If there's ever any question, I can place an ROI on them, and they'll actually have different absorption values. And then, for the purposes of the human eye, viewing these images that we're producing, we can influence contrast by changing the window level settings. Okay? And I think we've had an opportunity to mess with window and leveling, right, in this class. Okay. All right. Temporal resolution. Sometimes the word temporal, we think about the temporal bone or something like that. Temporal is, she talks about in the book, it can also be used to indicate time. So what this is talking about is timing resolution, right? And the major thing that impacts this is how rapidly the data is acquired. So with the early CT scanners, we were very interested in increasing their scan speed, right? Because as we increased their scan speed, we were going to have increased temporal resolution. One big impact in this, and when I think about MRI, for example, MRI has historically had bad temporal resolution. So MRIs of the abdomen have been limited because the patient can't hold their breath for 10 minutes while you do an MRI of their abdomen, right? In CT, I can do that same set of images in like 20 seconds. You should be able to hold your breath that time. But historically, this was controlled by gantry rotation speed, the number of detectors in the system. So if it was a single detector versus a multi-detector, that would increase. If it was a single detector, we'd actually see a decrease in temporal resolution because we would have to have the patient hold their breath longer. And the speed with which the system can record those changes. And it's reported in milliseconds. So we're talking about really, really rapid changes in time. So, here's a review question. The appropriate technique for a given patient was 200 mass. The technologist mistakenly used 100 mass. Which aspect of image quality would most likely be affected? Would it be spatial resolution, contrast resolution, or temporal resolution? Good. Contrast resolution. Insufficient mass will result in an increase in noise, which primarily affects contrast resolution. That's it for today.